Welcome to Six Sigma Black Belt, Course 5, Module 3, Parametric Hypothesis Tests. Hypothesis testing is most powerful when conducted under parametric constraints. There are a host of various applications that can be explored. In all cases, we must not only be mindful of the test and what it tells us, but also the assumptions that must be satisfied for each test. Let's start by discussing tests where we compare a set of data to a target parameter. When the population follows a normal distribution and the population standard deviation is known, then the hypothesis test for comparing a population mean mu with a fixed value can be described here. Note that there are two one-tail scenarios and one two-tail scenario. The null hypothesis is denoted by h sub 0, and the alternative hypothesis is denoted by h sub 1. The test statistic is given by the bottom equation. Here, x bar is the sample average. Sigma x bar is the standard deviation of the sample means. Per the central limit theorem, this is the same as the population standard deviation divided by the square root of the sample size. If the number of samples is greater than 30, the sample standard deviation is often used as an estimate for the population standard deviation. As an example, consider this set of data for the length of a plastic tube. Suppose we wish to test the claim that the average length is less than 9.25 inches. Assume that the population standard deviation is 0.35 and alpha is 0.05. We calculate the test stat to be 0.3930. The critical stat will be 1.645. Note that this is for an area of 0.05 in one tail. Since the test stat is smaller than the critical stat in magnitude, we fail to reject the null hypothesis. The length appears to be greater than or equal to 9.25 on average. The setup for the t-test is just like that for the z-test. However, the test stat is based on a student's t-distribution. The student's t-distribution applies to samples drawn from a bell-shaped population. Here, we are making inferences about a population mean, but the population variance is unknown and the sample size is small. The use of the t-distribution becomes less urgent as the sample size gets larger. Most texts give a sample size of 30 as the transition point between t and z. In practice, we should lean more toward t even if the sample size exceeds 30, but is still considered relatively small. Students' t is more conservative under these situations. Consider this example. Suppose the average puncture strength of a disposable needle needs to be 34 pounds. We collect a sample of 20 needles and find the sample average to be 31.7 pounds, with a sample standard deviation of 2.1 pounds. Can we be assured with 99% confidence that the needles are acceptable? The test statistic will be negative 4.898, and the critical stats are plus or minus 2.8609. Since the test stat is bigger than the critical stat in magnitude, we reject the null hypothesis. The lot of needles are not acceptable. When looking at averages of data, it is also important to understand the variance of the data. Variance can help us in making inferences regarding the population mean. Population variances are distributed according to the chi-square distribution. The chi-square test is widely used in two applications. First, comparing known variances, and second, comparing observed and expected of test outcomes when there is no defined population variance. The configuration of the null and alternative hypothesis for variance follows the same format as what we have seen with means. The test statistic for the chi-square test is given by the formula here. We will compare this to a critical chi-square statistic. Note that this statistic is based on an alpha and a degrees of freedom. Degrees of freedom is sample size minus 1. The chi-square distribution is not symmetrical. An alternative statement of less than would translate to a left-tail test. An alternative statement of greater than would translate to a right-tail test. Let's consider this example. Suppose we were looking at the variation of the glue strength of plywood. We make changes to the process and feel that this would deliver a standard deviation below 20. We measure 10 samples and get a sample standard deviation of 11.3. Because the sample standard deviation is less than the population standard deviation, we will have a left-tail test. The test statistic is 2.87. The critical statistic for alpha, 0.05, and 9 degrees of freedom is 3.33. Since the test stat is smaller than the critical stat, we will reject the null hypothesis. The process changes appear to have been effective. It is often necessary to compare the observed behavior of a situation to an expected behavior. This idea will be highly utilized in comparing the shapes of distributions in another type of test called goodness of fit. Let's consider this example. It deals with the frequency of counterfeit checks. Have you ever wondered how the government detects counterfeiting of checks? They use a rule known as Benford's Law. The table above gives the expected frequencies of Benford's Law as percentages of the leading digit of a check. Suppose the number of checks under investigation is 804. Based on the number of checks under investigation, we can take the product of this number and each percentage to get an expected frequency. The hypothesis test statement will be that the leading digits of the observed checks conform to the frequencies outlined per Benford's Law. The alternative hypothesis statement will be that at least one leading digit from the observed checks will not conform to the frequencies outlined per Benford's Law. Let's assume alpha is 0.05. The test statistic will be based on a square of the difference between each observed value and its corresponding expected value divided by the respective expected value. These calculations are then summed to get the test statistic. The critical statistic will be based on alpha as before, but the degrees of freedom will be determined through the product of the number of rows minus 1 and the number of columns minus 1. In the table above, we have taken the total number of checks, 804, times each percentage per Benford's Law to get the corresponding expected frequencies. Note that the precision of each expected value is retained for the entirety of the calculation. Rounding will introduce error and possibly affect our decision. The test statistic is 50.25. There are 2 rows and 9 columns. This gives us a degrees of freedom of 8. At alpha equal to 0.05, we find a critical statistic of 15.51. Note that this is a one-tail scenario and taken in the right tail. Since the test stat is bigger than the critical, we reject the null. There appears to be check fraud. When testing a claim about a population proportion, a proportion test can be used. We have a handful of assumptions that must be met. These align with the assumptions for the binomial discussed earlier. Independence of trials, constant success rate, 2 outcomes, and a finite number of trials. If n times p and n times 1 minus p are less than 5, we can apply a binomial behavior. If n times p and n times 1 minus p are greater than 5, then we can apply a normal behavior. The configuration of the null and alternative hypothesis for the proportion follow the same format as what we have seen with means and variance. The test statistic is given in the formula shown here. X is the number of successes, n is the number of samples, p sub 0 is the population proportion. Like before, a critical z statistic can be determined based on a known alpha and compared to the test statistic to arrive at the appropriate decision.